Okay, everyone, welcome to Quantum Diagrams, an introduction to the graphical language of ZX Calculus, Lecture 2, as part of the NITheCS Mini-school for March. Kishan will take us through Lecture 2 just shortly. I'm just going to reread his biography for those who didn't join us last time. Kishan is a postdoctoral researcher in the Quantum at Sun group at Stellenbosch University. He completed his PhD degree in mathematics at the University of Johannesburg in 2024. His current research focuses on categorical quantum mechanics, specifically quantum logic and ZX calculus. If you have any questions, please type them out in the chat or in the Q&A, and we will answer them after the talk. Thank you. Okay, Kishan, you may start. Thank you.
Thank you. I hope you can hear me. So I'm going to be continuing from last week's lecture where we introduced ZX calculus and we described how it arises as string diagrams in a category with suitable properties. So ZX calculus, we said they are diagrams representing quantum processes, and we said that they are string diagrams in a suitable category, namely a special commutative dagger Frobenius algebra. And these diagrams can be interpreted as linear maps in a well-defined way. So we have the category of Hilbert spaces with linear maps, and we know how to interpret these ZX diagrams in terms of that category. And ZX calculus also gives us rules or axioms on how we can rewrite these diagrams. In this lecture, we will be going through how to apply ZX calculus in practice, as last week I mainly introduced ZX diagrams as string diagrams and certain rules. However, in practice, we use forms of these slightly focusing on that today. So just as a reminder, our quantum circuits, we said we can draw them like this, and by convention in this talk at least, we're going to be reading them from bottom up. And here our Y's represent our qubits, and these boxes represent quantum gates. And putting two of these diagrams next to each other represents our tensor product for combining these two systems. So as a reminder, the language of ZX calculus is in terms of what we call spiders. So here we have a green spider. It has n inputs and m outputs, given by the wires going into and coming out of our spider. And it's colored in green, and it has a phase alpha written into it. Now, the way to interpret this spider is by this diagram here, where we are working in the Z basis, or the computational basis, which is the 0, 1 basis on your block sphere. And here we have e to the I alpha, denoting that phase alpha. Another convention is that when we don't write in a phase, we take it as phase 0. So that was the green spider. The red spider is defined almost the same. However, now we are working with the X basis, so the plus minus basis on your block sphere, and it's defined almost identically. A reminder from last week, why it's because they form what we call strongly complementary bases, a set of strongly complementary bases. And all this means is that when we measure in one basis and the other, and then the other, it doesn't matter if we switch the order. It doesn't matter if we switch the order. Some other notation that we will be using. So our special diagrams for states is this triangle with one wire coming out. Effects are this triangle here with one wire going in. Scalars is given by a state and then followed by an effect. This can be seen as a form of measurement, and we combine them and write a scalar as simply a diamond like this. Why did we do this using these triangles here? It's because if you rotate by 90 degrees, you get the usual Dirac-Braket notation. We also have these special spiders here, so a red or green spider with one wire going in and one wire going out. And these correspond to the identity map which we write as simply an empty wire like this. We also have these cup states. So in last week, I explained them in terms of string. And we do think of it as an effect. So also in this case, it doesn't matter if it's red or green, it turns out to be equal. So a universal set of gates for quantum circuits is the Z rotation, the controlled NOT gate, and the Hadamard gate. It turns out that your Hadamard gate, given by this yellow box with an H in it, can be decomposed in terms of Z rotation and X rotation as given by the diagram on the left. It's also clear that our Z and X rotations can be written in terms of spiders as simply a spider with one input wire and one output wire and a phase alpha and beta. These two are switched. That's a typo. And these correspond to our Z and X rotation, depending on the color of your spider. Our controlled NOT gate is also can also be written as a ZX diagram in this way. We have this green spider and red spider and one wire connecting them. This shows that any Z rotation, the controlled NOT gate, as well as the Hadamard gate can be written very simply in terms of a ZX diagram. And hence, any quantum circuit can be transformed into a ZX diagram by writing your gates in terms of these spiders here on the right-hand picture.
I'm a bit confused. I thought from the previous slide that if you have only one wire going in and out, then it's the same as the idea.
That was with no phase, so zero phase. This has phase alpha. Okay, so we have ZX calculus is universal because we can convert any quantum circuit into a ZX diagram. However, it's also complete. Anything you can prove about linear maps, any equality you can prove about linear maps in the category of Hilbert spaces with linear maps, you can prove them using ZX calculus rules. And that was a major result that was proved in 2019, if I'm not mistaken. So now I'll briefly recap the rules of ZX calculus. And in certain cases, I'll give you alternate forms of their rules, which we will see why we take these alternate forms when looking at examples. So the first rule is spider fusion. If we have two spiders of the same color connected by some number of wires, you can fuse the two spiders together and their phases are added. And this works for red and green spiders. Based on spider fusion, we note some key things that that for these diagrams, in a certain sense, only the connectivity matters. So what do I mean by this? We can, in fact, deform these diagrams and still obtain a diagram equivalent to the original one. For example, the diagram on the right here, all we've done is bend this wire between the red and green spider and rewritten it that way. And it turns out this is equivalent to the original diagram. The picture on the diagram on the left gives us a more surprising property that when we're working with these spiders, it doesn't actually matter whether we're considering a wire as an input or output, as we can convert one to the other. For example, on the leftmost green spider, if we take the output on the right here, or the rightmost output, we can in fact consider it as an input in the following way. So step one is you unfuse a green spider. So we're introducing another green spider whose output is precisely that original output we considered, and we connect this new by fusion. By the fusion rule, we see that these two diagrams are the same. Once we've done that, we can also extend this new spider. We can pull it down to draw it as a cup like this, and we don't need to actually draw this green spider here. And in this way, we get this diagram on the right here, and we see that the original wire that was an output has been converted to the input, to an input. However, we have to keep track that we've done that, and now we have this cup here that we've introduced. So there are tricks like this that are common when working with ZX diagrams that we need to be aware of. The next rule is called leg chopping, or the Hopf rule. And it says that if we have two spiders of different colors connected by two wires, then those two wires connecting them can be removed. So in the previous rule, we saw that when spiders of the same color were connected, we can fuse them. But now if they have the opposite colors, we can simply remove the two wires connecting them. It turns out actually that this rule can be derived from the remaining rules, and I'll explain that later on. The next rule is cupping. So if we have a red state connected to a green spider with only that one input, all that happens is we can rewrite this as copies of that red state with the number being the same number as the outputs of your original green spider. And the dual case happens if you have a green state going into a red spider. Now, it's important to note here that I didn't include any phases here, so you can't use this for any phase. However, this works for phase 0 or phase pi. I didn't include the phase pi, but as that's not as common, so we can think of this as simply the rule that we need to be aware of. The next rule is the bi-algebra rule, which I introduced last week as the diagram on the left here. When we have two green spiders and two red, each green spider is connected to each red spider and vice versa, then we can simplify this diagram in the following form. We have one red spider, one green spider, and a single wire connecting them, and the colors have flipped vertically. So that's how I introduced this last week in terms of string diagrams. However, we can actually show that this rule here is equivalent to the form on the right. The form on the right says if we have a square with alternating green and red spiders, we can simplify it in the following way. Note that it's often useful to label each vertex or each output or input wire of the vertex. And all that happens here is on the left-hand side, the two spiders, the colors are flipped. The right-hand side vertices disappear, and the wires into the right-hand vertices are swapped.
How do we know which wires are in this output?
As I said, we read it from bottom up. However, as I explained, that it's not as important to remember what's an input or output, but by convention, we read it from bottom up. So in this case, 4 and 3 would be inputs and 1 and 2 would be outputs.
And the connecting ones?
These connecting ones, as I said, only the connectivity matters. So for example, this vertex near the 2 here, you can pull it up. So this wire could be seen as an input, or you could have it as an output, depending on how you draw the diagram. We also have the color change rule, which says that if I have a green spider and I put a Hadamard gate on each input wire and each output wire, then the Hadamard gates disappear and the color of the spider swaps. And that happens for both green and red spiders. Now, as I said before, we can actually derive the leg chopping rule or the Hopf rule from the remaining rules. And this is what we'll show now. So the leg chopping rule said if we have a red and green spider connected by 2 wires, then we can remove the 2 wires between them. And that's what I'm going to try and prove. However, instead of arbitrary spiders, I'm taking a green spider with 1 input and a red spider with 1 output and 2 wires connecting them. And I'm showing that we can, in fact, remove these 2 wires. And we're going to be proving this. So how do we prove this? Step 1, on this right-hand wire connecting the 2 spiders, we introduce 1 green spider with 0 phase and 1 red spider with 0 phase. I can do this because remember we said an identity wire or an empty wire is simply a red wire output. So adding this red spider here is simply indicating identity. And similarly for this green spider, I think someone raised their hand. You can go ahead and ask a question before we continue. Okay, so he says it's fine. So all we've done is introduced identity here, or indicated identity here. From here, we can unfuse spiders. So to this green spider, I add a new green spider connected to it, and the same for the red spider. And we see that this third diagram here is equivalent to the, or equal to the second one if we fuse these. So what I'm doing here is the opposite of fusing, so unfusing. And now once I have this third diagram here, we see that there is a square here with alternating red and green spiders, and we can apply the bialgebra rule in the form of the square. And when we're talking about the bialgebra rule for squares, we call it square popping. So if we do that square popping rule, we get this diagram right here. It says that the 2 spiders on the left, their colors flip, and the 2 vertices on the right disappear, and the wires into those 2 vertices are swapped. So we'll get this rightmost diagram. So currently we have the diagram on the bottom left of this slide. And now to simplify further, we would like to use the copy rule. The copy rule says if we have a red state going into a green spider with n outputs, we can simply copy that state n times. So in this bottom left picture, we do see we have a red state going into a green spider here, but this green spider has an additional input. It has an additional input wire. So we'd like to simplify that portion of this diagram, which is what is done on the top half of the slide. So on the top half of the slide, we have a green spider with 1 red state going in and an additional wire going into it. We want to use the copy rule here. So in this case, we do that same process of making this input and output. So this left-hand wire going in, all we do is we rewrite it here as an output, and because we've swapped it, we have to indicate a cap here. Once we've done this, we now see that we can apply the copy rule, and it says that I will now have 2 copies of this red state, and namely it's connected to each wire going out of the green spider. So we'll have this third diagram here. And now I can simply straighten this red spider connected to this cap to get this last diagram here. Notice when I say straightening, this follows from the properties of string diagrams that we discussed last week, where we had what we call the snake law or the yanking law, where when we have these things, we can straighten them. So once we have simplified the top diagram into this 1 red effect and 1 red state at the top, we can substitute that into the corresponding portion of the diagram on the bottom. So the corresponding portion we said is this green spider on the left here, with one wire going in and the red state going into it and one wire going out. If we are going to substitute this into it, we get this diagram here. So namely, a wire going out of your green spider becomes a red state, and this wire going in becomes, we connect this red effect, get this diagram here. Once we have this diagram, all we do now is fuse these two red spiders together. We fuse this red spider to the bottom one to get this diagram. And once we are here, we now see that this red spider at the bottom is simply an identity map. So we indicate it by the empty wire. So we simplify to get this rightmost diagram at the bottom. And this is what we wanted to prove when we have a green spider connected to a red one with two wires connecting them. We can remove the two wires, which is exactly what has happened here.
This result only true when bases are 0.
Yes. Because, for example, I said the copy rule only works when phases are 0 pi, so this works when everything is 0.
So the leg chopping rule is only applicable to phase 0 as well.
Yes. And an example that I briefly showed last week is when we have 3 alternating controlled NOT gates, and we want to simplify that. I think it's very well known in quantum circuits that if you apply 3 controlled NOT gates in sequence, all it is a swapping rule. And you can prove this very easily using ZX calculus. So we said a controlled NOT gate is a green spider and a red spider connected horizontally on the 2 qubits. And if we have 3 of them alternating, we have this diagram on the left. And if we want to use ZX calculus to simplify this diagram, the obvious step or the obvious rule to choose here would be square popping. As we see, we have 2 squares in this diagram. It's in fact easier to choose this top square. However, you could have started with the bottom one. So I chose the top square and I'm going to apply square popping. So I've labeled my vertices and applied the square popping. So remember, vertices 1 and 4, their colors swap, and the 2 wires going out of these 2 vertices get swapped. And that's how I get this. The second diagram. To get the third one, all you do is you fuse the 2 green spiders connected to each other and the 2 red ones connected to each other to get the third diagram. Once we have this third diagram, now we use leg chopping because we see that we have a green spider and a red spider connected by 2 wires. So those 2 wires can be removed. And then lastly, this green and red spider has 1 input, 1 output, and has 0 phase. So they are actually identity wires, and hence we indicate by an empty wire. So we get this last diagram, which we can clearly see is a swapping rule. A more complicated example, and this rule is in fact implemented in compilers making use of ZX calculus or inspired by ZX calculus, is this example here. So suppose we have this diagram on the left. It's 2 green spiders on the left wire, 2 red spiders on the right wire, and a green phase gate in the middle of the 2 red spiders with phase alpha. We want to simplify this diagram. So here, how would we simplify such a diagram? We actually want to force a situation where we can apply one of the rules, as here the only rule you can apply is fusing these 2 green spiders, and that's what we start with. So we start with fusing the 2 green spiders here, and after this, we need to force one of the rules. There's an alpha missing in this green spider. If the alpha wasn't there, this is just a square, and we could have made use of square popping, but there should be an alpha here, and you can't make use of square popping with arbitrary phases. So what we do is this green spider on the left, we unfuse it. So we introduce a new green spider connected to it and connecting to everything going out of it to get this third diagram here. And on this third diagram here, we still can't make use of square popping as we have this green spider has phase alpha. So what we are going to do is unfuse again to get the fourth diagram. We take the alpha and we take the alpha to the right and we introduce a new green spider here. And now we see that it forms a square and we can do square popping. So that's precisely what we do. You label your vertices clockwise here and apply square popping to get this diagram. Once we have this diagram, all we do is redraw it to get our output here. So this is how we are able to simplify this slightly non-trivial diagram into the rightmost one. However, here there's, if we are thinking in terms of quantum circuits, it's not completely clear as to how to represent this using quantum gates. So there is a topic in ZX calculus called circuit extraction, which says that we do not know after applying our ZX calculus rewriting rules whether our result will represent some quantum circuit. So we don't know whether that's true in general. However, there are certain graph theoretic properties that we can impose on these diagrams considered as graphs to ensure that the diagram does represent a quantum circuit. And there's this diagram rewriting in such a way that these conditions are satisfied in each step. So that these conditions are called G flow and C flow, and I'll speak a bit more about that in the next lecture.
So you know that there are other circuits, other diagrams, which you know that there is no circuit that represents it.
Yes, because these diagrams work for any linear maps. However, for quantum circuits, it only uses unitary maps. So it should be expected that.
And does it mean that this calculation then is valid from the point of view of quantum circuits? Because we got something that we could represent as a circuit.
It's valid for Hilbert spaces and linear maps. However, our result, we don't know whether it's true that it comes from a circuit. It's true that, you know, the map that it represents, the linear map that it represents, corresponds to the leftmost one, corresponds to the rightmost one. However, we don't know whether, you know, our result still represents a circuit. So now some more examples based on this theme. So if we have this diagram here, you can see on the left two wires, we get that pattern from the previous example, and we continue the pattern on the right, so connect these green spiders to red spiders horizontally. We can use the previous example and apply the result of the previous example to rewrite the square here with this alpha phase gate included to get this portion of the second diagram. So that's all we've done is apply the previous example. And now once we've done that, we can do fusion. So on the middle wire, we can fuse all the green spiders. And on the right wire, we can fuse the two red spiders to get the third diagram. Once we have the third diagram, we can use leg chopping and remove these two wires, as well as show that the rightmost wire then ends up to be an empty wire or identity wire to get the rightmost diagram. So that's one variation on the previous example. Another variation. Sure.
How can you tell the compiler that's you will see there are some programs, but
Yeah.
how can you tell the compiler that the last thing is back to the configuration?
Okay, so
in these cases, that the last picture is easier or better than stuff.
So I'm not sure what exactly, there are conditions, I think, in quantum circuits that something is more, you know, efficient in quantum circuits. But I don't have a clear answer on that. But for example, you can tell, for example, that there's less gates on the rightmost spider. And that's maybe something that's more efficient,
Yes.
which is easy to tell. So this next example is a variation on that first example as well. However, this is a bit more non-trivial. So in this example, on the middle and right wire, we have that same pattern from the first example, namely green spiders connected to red spiders horizontally and a green alpha phase gate applied in the middle. And now on the left, we're continuing this pattern. And this turns out to equal this right-hand diagram where the three individual wires have one green spider, and we have a red spider connected to each of these with the alpha phase gate connected to the red spider. And how would we prove something like this? Again, to that original pattern. So on the middle and right spider, the original example can be applied here. So that's what we do initially. So we represent this middle portion here with what we obtained in that first example to get the second diagram. Once we have this, again, we want to force a square in some manner so that we can apply square popping. So what we do is on the leftmost wire, we fuse the two green spiders, and then we fuse them vertically and then unfuse horizontally to get the next diagram. Once we've done that, we do see that a square forms here, which you can label and do your usual square popping to get this diagram here on the square. So 1 and 4, the colors switch. 2 and 3, the vertices disappear, but the wires that go into them are swapped. And that's all that's happening from this diagram to this one. And then once we have this now, we immediately get our result because this red spider here fuses with this one, and redrawing it obtains the result. In fact, this pattern, when we continue this type of example, when we continue the pattern, adding wires on the left, holds in general. So for four wires, this would be the pattern of that example, and it does equal the same pattern as the last example. So here we have 4 wires, each with a green spider, 1 red spider connected to all of them, and this green alpha phase gate connected to that red spider. And in general, you can prove this for any number of wires for this specific pattern using induction, for example, using ZX calculus. I think this shows how powerful these rules are. So the next thing I want to discuss is a quantum teleportation protocol in terms of ZX calculus. And I think this is one of the topics that, motivated this graphical language of ZX calculus. In fact, the diagram I'm going to show in one of the next slides was drawn even before ZX calculus was introduced. So for quantum teleportation, we need an entangled state. So we want one of our Bell states, and these Bell states are shown on the slide here. So we have these cap states. However, we could have phase 0 indicated by the first diagram, a green pi phase, a red pi phase, or this last diagram with a green pi spider and a red pi spider. So these correspond to our usual Bell states. And now the question of quantum teleportation is that Alice and Bob share Bell state, and Alice also has a qubit in state psi, and Bob needs that state. How do we pass the state to Bob without physically sending it to Bob? And that's the question of the quantum teleportation. Just one small note to make here is that I'm choosing one of those specific Bell states, so namely the first one, but you could modify it in terms of the first one. So how would we do this using this diagram? How would we send the state psi to Bob using this diagram? The answer comes from something we discussed in the last lecture is that if we apply this cap here, connecting psi to this entangled state, this corresponds to taking a measurement along the Bell basis, and we obtain this cap followed by this cup, or something that we called a snake in the last diagram. If we were able to do this, then we could simply slide the state psi along this diagram to Bob. And this follows from the string diagram rules I mentioned in the last lecture, namely that when we have a diagram of this form, we can slide a map F along it. And that followed by something we defined as the name and coname of F. So if we were able to do this, we could slide the state psi to Bob and we'd be done. But adding that cap here is essentially measuring along your Bell basis. And it would introduce what we call a Bell effect. So doing this would introduce a green and red spider here. And there's 4 possibilities. So you could get 0 or pi in the green spider and 0 or pi in the red spider as your phases. And once these phases are included there, we can no longer slide psi over them to Bob. So there needs to be some type of correction that happens before we can slide. So what we do is we look at this red spider. If it's state 0 or pi, on Bob's side, we include a red spider with state 0 or pi, which is the same as the observed state here. If we do that, what we see then is if we slide this red spider now to Bob, it would cancel because in both cases, the phase would be 0 or 2 pi, which are equivalent. Once we've done that for the red spider, we do it for the green spider as well. So we do the exact same thing. If it's 0 pi here, we include another one, which is 0 pi on the right-hand side, on Bob's side. And doing that, we see that this we could slide these two and they'd cancel out and we'd be fine. But how would Bob know which phases to include here? This is where we'd have to use classical communication from Alice to Bob to inform him which phases are observed here, so he knows which to include on his side. So once we've done that, we can successfully cancel out the green and red spiders here, and then slide the state psi along to Bob, and Bob would now have the state psi, and that's the quantum teleportation protocol in terms of ZX diagrams. So just to end off, what are some further applications of ZX calculus? It turns out it's a useful language to describe what is called measurement-based quantum computing. So the idea of measurement-based quantum computing is that instead of applying a phase gate to a state, what we're actually going to do is take a measurement along some basis, and the effect will be the same as the effect of applying that gate. So what do I mean by this? For example, this diagram on the left here, this leftmost diagram, we see we have a qubit in state psi and a red state here, which corresponds to our plus basis in the x basis. And we apply one C0 gate, and then we take a measurement and obtain an effect alpha. So that's the leftmost diagram. By our rewriting rules, we can fuse the two red spiders. It turns out to be identity. This green alpha effect, we can fuse it with the green spider below it, and then straighten the wire to get this diagram next to it, which is simply the state psi and then an alpha phase gate applied to it. This is interesting because on the leftmost diagram, we haven't applied any phase gates. However, on the right-hand diagram, we see that it becomes an effect of this measurement here. And that's why we call this measurement-based quantum computing. However, as we saw in the quantum teleportation protocol, we see that we might have two options for our effect. When we measure along a certain phase, we could get alpha or pi plus alpha. And then we wouldn't be able to get just alpha as our final goal. So what we'd have to do is account for correction if we wanted the phase gate alpha to be our result. So if it was alpha, then we include a 0 or identity here. But if it was pi plus alpha, then we include a green pi phase here. And this would use classical communication to know which correction to apply here. And again, we get an alpha phase gate applied to the state psi. And just one further example of measurement-based quantum computing. So any phase or any gate applied to one qubit in a state psi, you can represent using such a diagram here. And just to note that two green spiders with the Hadamard gate between them is what we call the control Z gate. So if we have these controlled Z gates here with some effects occurring with alpha, beta, gamma, we can actually redraw this diagram using fusion to this right diagram here. So the alpha, beta, gamma, and this zero phase, zero effect spider gets fused to the spider vertically below it to obtain the right diagram, the diagram on the right. From there, we use the color change law. So this beta spider has two Hadamard gates on its input and output. So we change its color to red. And similarly for this zero phase spider on the right here. So we change its color to red to obtain this next diagram. And from here, we simply write the identity, this red and green spider's identity wires, and straighten the wire to get this rightmost diagram. And this, you can write any quantum gate in this form on one qubit. And this shows that by doing measurements, we can represent any quantum gate on one qubit in this form. And I'll end off with some references. I think the main reference we should look at is picturing quantum processes. It's number 3. So number 3 has it's a complete reference to all topics on ZX calculus. However, some more basic notes on this topic is 1, 3, and 4. And I'll stop here. So if anyone has any questions, I'll be happy to answer.
Ask a question. If you go a few slides back, where you explained the interpretation. Why was it necessary to introduce those green and red spiders in order to perform the interpretation?
So when we make a measurement, we get an effect as an outcome, and that's what's happening here.
So who is making the measurement? Alice is making the measurement.
Alice is measuring because it's on her side.
Why does Alice measure?
Because this red and green spiders appear on her side, and then
But
because of
have them. So
but they will appear. So that's a problem because now we can't slide the state to
they
Bob.
will appear if Alice measures it, right?
Sorry?
They will appear if Alice measures it.
Yes.
But why does Alice need to measure it?
To add that cap, it automatically appears. When you do a measurement, you get an effect.
So what is the
The
actual
only
physical?
way to add the cap is to measure.
And we're measuring along the bell base.
So Alice needs to measure this phi in order for it to be teleported to Bob. Is that correct?
She's making a joint measurement of the entangled one and psi.
So what is the actual physical process that's corresponding to this diagram? What are they actually doing?
Depends on the setup. Depends on how you set up quantities.
Can you give an example of?
So in photonics, Measuring means observing the photon one arm, two branches. If you measure it here, you know it's on the other arm as well. That's what they're doing. That's measurement. For the math is just seeing it, so you're just collapsing it down to one of the positive. Or what it is mathematically, that depends on the.
And just maybe one correction that I realize now is that when I introduced these red and green spiders, I call them strongly complementary bases. And I said that it doesn't matter which measurement you do, you can switch them. And I said the opposite thing. It's actually complementary means it does matter. They're the maximally incompatible ones. So it means you can't switch the order. Just to, correct that.
You mentioned at some point that everything which can be proven about Hilbert spaces and linear maps can be proven in this language.
Yeah.
Do they know that everything which can be proven in this language can be proven about linear maps, Hilbert spaces?
Yes, because you can get a functor from this context to Hilbert spaces.
You just check that the axioms hold,
Yeah,
Dutch rules hold. Well, that's the easier part.
yeah,
Well, it's the other way.
yeah. The other way is the harder. Not sure if the questions online.
Sound is always easy.
So I don't see any
Okay.
questions on. Sorry. Okay.
Okay, if there are no more questions online, I think we can call it a meeting there. Next week, Wednesday, will be the third edition of this lecture series. We look forward to seeing you there, and hopefully Prof. Francisco will take over from me next week. Thank you for coming, and have a good day, everyone. Thank you.